What if I told you that carrying the one in subtraction is basically a lie?
I mean, it is a complete lie, yeah.
Right. So think back to sitting at your elementary school desk, pencil in hand.
Just kind of sweating over a worksheet.
Exactly. You probably spent hours learning to cross out numbers, write little ones in the margins, and just like borrow from the next column over.
And we tell kids to do this, and then we wonder why so many of us grew up with this profound math anxiety.
It's so true. But you never actually borrowed a number in your life. And the fact that we were taught these invisible, frantic tricks just to get a fast answer is, well, it's something we are completely dismantling today.
Yeah, because that anxiety comes directly from treating math like a high-speed performance instead of, a language.
Which brings us to our deep dive for today. We have a really fascinating source, a family guide to grade 3 mathematics based on the Japanese curriculum called the Number Lantern.
Right, and the mission of this source isn't to just relearn your times tables or race through a stack of flashcards.
Thank goodness, because I hated those.
Same. The goal here is to notice what stays the same in the physical world, what changes, and how quantities actually fit together. And maybe the most profound shift is the baseline assumption that a corrected mistake is not evidence of a failure to learn.
Wow.
Like a corrected mistake is the actual evidence of learning.
Okay, let's unpack this. Because viewing math as a toolkit for understanding reality rather than a list of arbitrary rules, it completely changes how you process information as an adult.
It really does.
So we can start by tearing down this idea that numbers are just abstract symbols floating in your head.
Right, right.
The base 10 system, the system we use every single day, is just one powerful, repeating physical pattern.
Exactly.
10 ones make a 10, 10 tens make 100, 10 hundreds make 1,000. It just scales infinitely.
It scales perfectly, provided you understand the structural integrity of the number 0.
Yes. Let's talk about 0.
Most of us were taught to treat 0 as simply nothing. You read a 0, you ignore it, you move on.
Which is such a mistake.
A huge mistake. 0 is highly structural. If you look at a number like 4,006,090, so 4,006,090, those zeros are not empty space. They are load-bearing pillars holding the other digits in their proper physical locations.
Right, like there are no 100,000s in that number, but the 100,000s place still absolutely exists.
Exactly. 0 is the placeholder that prevents the entire base 10 structure from just collapsing into a pile of digits.
And recognizing that every number has a physical place completely alters how you approach something as basic as subtraction.
Oh, totally.
Let's go back to that borrowing a 1 lie. I distinctly remember my teacher telling me to just go next door and borrow a 10.
Which is incredibly imprecise language. You are not borrowing anything because you have zero intention of giving it back.
No, I'm keeping it. You are trading.
You are trading, yes. Let's make that invisible thinking visible for a second.
Okay.
Imagine you are trying to subtract 786 from 3002.
Okay, if I just line those up vertically on a piece of paper, and try to subtract down the columns, I hit a wall immediately.
Right, because you cannot take 6 ones away from 2 ones.
I just can't. So my instinct is to look to the tens place to borrow. But in 3002, the tens place is a 0.
It's empty.
The hundreds place is another 0.
Also empty.
I have to travel all the way over to the thousands place just to find a number.
And if you use the language of trading, you stop doing a blind magic trick and start doing an actual exchange of value.
Okay, walk me through that.
So you take 1,000 and you trade it in for 10 hundreds.
Okay.
Then you pause. You take one of those hundreds and you trade it for 10 tens.
Right, right.
Pause again. You take one of those tens and you trade it for 10 ones.
So now I finally have 12 ones in that final column.
Exactly. And now you can comfortably subtract the 6.
It's literally like taking a crisp $100 bill to a bank and asking the teller to break it down into 10 tens.
Yes.
And then breaking one of those tens into 10 ones just so you can hand someone exact change.
Yeah. That is the perfect analogy. It makes complete logical sense.
It really does. But then the guide moves into multiplication. And I'm going to push back on this.
I know. Okay, lay it on me.
Because I remember looking at the visual area model for multiplication in the sources and thinking it seemed exhausting.
The rectangles.
Yes. If you want to multiply 36 by 24, they have you draw a literal rectangle.
They do.
You split the top line into a segment of 30 and a segment of 6. You split the side into 20 and 4.
Right.
Then you calculate the area of the 4 smaller boxes you've created, which gives you 600, 120, 120, and 24.
Yep, the partial products.
Right. And then you add those 4 chunks together to get 864. I mean, why on earth would anyone draw a box when the standard stacked algorithm is a fraction of the time. Next time I calculate a tip or split a bill, I'm not drawing a rectangle on a napkin.
Okay, fair enough. You might not draw it, but your brain needs to visualize it. What's fascinating here is that the area model and the written stacked algorithm aren't separate rules.
They aren't.
No, they're the exact same concept. It's distributive reasoning.
Meaning you distribute or like break apart a massive calculation into smaller, bite-sized chunks.
Exactly that. You break a hard problem into friendly pieces.
Okay, I guess that makes sense.
The reason the visual box is so critical early on is that it prevents a massive systemic error.
What error?
Well, when people just stack 36 on top of 24, they multiply the 4 by the 6 and then the 4 by the 3, right?
Yeah, that's the first row.
But when they move to the bottom row, they often multiply the 2 by the 6 and just write down 12.
Oh, they forget to add the 0 on the end of the second row. I did that constantly.
We all did, because the standard algorithm obscures the truth. It makes you forget that the 2 in 24 does not mean 2.
Right.
It means 2 tens or 20.
Oh, wow.
The visual area model makes it physically impossible to make that error. You are explicitly looking at a box labeled 20 on one side and 30 on the other.
And 20 times 30 is 600.
Exactly. The visual model forces you to respect the magnitude of the numbers. You aren't just shifting digits over one space because a teacher told you a rule.
Right. You are doing it because you are multiplying actual physical tens.
Exactly.
The numbers mean something physical, like the floor plan of a house, which is honestly the perfect bridge to the next major concept we found in the sources.
The idea that naked numbers are useless.
Yes. A naked number is completely useless. Numbers require human context.
The guide states this so clearly. Every number needs a label.
Right. Like the statement, the ribbon is 4, is an unfinished thought.
Exactly. Are we talking about 4 meters, 4 centimeters, 4 separate ribbons?
You have no idea without the label.
Yeah.
If you were told that 32 apples are packed 8 in a bag, and you do the arithmetic, so 32 divided by 8 equals 4,
Right.
that 4 doesn't magically mean 4 apples. It means 4 bags.
Yes. The math is just a tool we are using to describe the physical objects in front of us.
Which blew my mind, honestly.
Well, and the physical reality in the room can completely alter the meaning of the math, even when the arithmetic is identical.
Oh, like the two meanings of division.
Yes. Consider how division has two entirely different real-world meanings. Sharing versus grouping.
I had to read this section twice because my brain had entirely merged these two concepts together.
So many adults do. Walk us through the difference.
Okay, picture 24 markers.
Got it.
If you want to share them equally across 6 tables, you are trying to find the amount in each group. You deal them out one by one.
Like dealing cards.
Exactly. So 24 markers across 6 tables equals 4 markers per table. That action is sharing.
Right.
But if you have those same 24 markers and you are placing them 6 to a bin, you are now measuring how many groups will fit.
You're taking a chunk of them at once.
Right. You grab a handful of 6, put them in a bin, grab another 6, put them in a bin. 24 markers, place 6 to a bin equals 4 bins. That is grouping.
And the fascinating thing is, the number sentence on the whiteboard 24 divided by 6 equals 4 is totally indistinguishable.
They look exactly the same.
But the human movement happening in the classroom is completely different.
And that human element really takes center stage when division doesn't work out perfectly.
Ah, yes.
Remainders.
We have to deal with remainders. And how you handle the leftovers depends entirely on human interpretation.
The remainder dilemma.
Yes. Think about this scenario. You have 31 people who need a ride to an event, and you have vans that hold 6 people each.
Okay, so you punch it into a calculator. 31 divided by 6 is 5 with a remainder of 1.
Right. But what is the practical human answer?
The human answer is 6 vans.
Exactly.
That one remaining person cannot be left standing on the curb just because the arithmetic output a remainder of 1. You are forced to round up and secure a 6th van.
Now take that exact same arithmetic and change the real-world materials. You have 31 beads, and you are making bracelets that require 6 beads each.
Okay, so 31 divided by 6 is still 5, remainder 1.
But in this reality, the practical answer is 5 bracelets.
Right, because that one leftover bead is useless on its own. You can't magically stretch it into a 6th bracelet, so you simply ignore the remainder.
It highlights a profound truth about applied mathematics. Arithmetic is just the engine.
The human brain has to steer the car across the finish line.
Yes.
It's like packing a suitcase for a trip.
Okay, I like this.
The mathematical volume of your clothes might perfectly match the interior volume of the suitcase.
In theory, it fits.
Right. But context tells you if those clothes are bulky sweaters that require you to physically sit on the luggage to zip it shut,
Right.
The math doesn't zip the bag. You do.
And if the human brain is the final interpreter of context, we need a way to know if our brain has completely malfunctioned during the calculation process.
We need steering wheels and guardrails.
Yeah.
Mental tools to keep us grounded in reality.
Exactly. I spent my whole life thinking of estimation as the lazy way out.
Oh, me too.
Something you do when you just don't feel like finding the real answer. But reframing estimation as a guardrail is brilliant.
Because a guardrail keeps your car from flying off the cliff.
Yes. If you are adding the numbers 186 and 74, your brain should immediately do a rough scan.
So 186 is close to 200.
And 74 is close to 70.
So the final answer absolutely must live somewhere near 270.
Right. If you do the exact calculation and get 260, that feels safe. It's inside the guardrails.
But if you misalign your columns on the paper and end up with an answer of 2600,
You shattered the guard.
you instantly know you made a structural error.
Yeah.
Because 2600 makes 0 sense given the starting materials.
You catch the mistake before it becomes a consequence.
No.
And speaking of places where people constantly shatter the guardrails, we have to talk about measuring time.
Oh my gosh, yes. Calculating elapsed time is a massive trap.
Because time does not care about base 10.
It really doesn't.
Time is stubbornly base 60. There are 60 minutes in an hour, not 100.
Right.
If you try to use the standard stacked subtraction method for a time problem, you are going to crash.
I actually tried this when I was reading the notes.
Did you really?
I did. I wanted to find the difference between 9.45 and 10.15. So I stacked 10.15 on top of 9.45 and just subtracted straight down as if they were normal numbers, treating the hour mark like it was 100 minutes.
Oh, no. And what did it say?
The math told me the gap was 70 minutes.
Which is wildly, dangerously incorrect.
It's 30 minutes, 15 minutes to reach 10.0 and 15 minutes past the hour.
Exactly. This is why you cannot use base 10 algorithms for time. You have to use a timeline.
A literal physical number line where you can visually track the jumps.
Right. You jump forward to the nearest hour, then jump the rest of the way.
You have to use the tool that fits the reality of the unit you're measuring.
The tool shapes the thinking. And we see the ultimate expression of this in the soroban, the Japanese abacus.
Oh, the abacus.
It takes all of this invisible mental math, the trading, the base 10 structure, and makes it entirely physical.
The soroban blew my mind, but I will admit I was incredibly confused at first.
It's intimidating if you aren't used to it.
It really is.
Yeah.
I couldn't understand how moving wooden beads could possibly be superior to just writing numbers down.
Well, picture the layout. It's a visible place value system.
Okay.
You have vertical rods representing one's tens, hundreds, thousands. On each rod, there is one upper bead, which holds a value of 5.
Just one bead worth 5.
Right. And below a central dividing bar, there are 4 lower beads, each holding a value of 1. You only count the beads that are pushed toward that central dividing bar.
And an empty rod-like, where no beads are touching the center, is a physical placeholder for 0.
Exactly.
Here's where it gets really interesting, though. The genius of it didn't click for me until I tried to do mental math adjustments.
Walk me through it.
Let's say you have the number 23 set on the abacus, 2 beads pushed up in the tens column, 3 lower beads pushed up in the ones column.
Okay, 23. Got it.
Now I want to add 4. My brain says just add 4 more ones. But when I look at the ones column, I only have 1 lower bead left resting at the bottom.
Right, you physically cannot push up 4 beads.
The physical limitation of the tool stops you from doing bad math. It forces you to make a trade, using the complement to 5.
Which means to add 4, you are forced to pull down the upper 5 bead to the center.
Right, and push away one of the lower 1 beads, add 5, take away 1.
The net result is adding 4.
But the abacus makes that abstract mental adjustment totally tactile. You literally feel the numbers trading places under your fingers.
You are building physical muscle memory for how parts make up a whole.
Yes.
And once you master how whole quantities fit together, the natural next step is figuring out how fractions of a whole fit together.
Which means we have to talk about fractions. And I know the immediate image everyone conjures in their head is a circle cut into pizza slices.
Oh, the pizza slice metaphor. It is a classic, but it is deeply flawed for long-term mathematical thinking.
Why is that?
Try to imagine 7/3 of a pizza. Your brain breaks trying to visualize a circle that is overstuffed with pieces.
That's true. You just picture multiple pizzas.
Right. The circle creates a dead end in understanding. Instead, the guide emphasizes placing fractions on a linear number line.
So if you want to understand 3/8, you draw a line from 0 to 1, and you divide that physical distance into 8 equal intervals.
Exactly. The third mark on the line is 3/8.
It proves that fractions are actual numbers with specific locations in space. They aren't just pictures of food.
Furthermore, the number line reinforces that the context of the whole dictates everything.
Right, like 3/8 of a giant outdoor vinyl banner is a massive amount of material,
Right.
but 5/8 of a tiny index card is practically nothing.
You cannot compare the fractions if the unit they belong to, the whole, is different.
That makes total sense.
And understanding scale and units brings us to the ultimate application of all these skills: reading data.
Organizing and interpreting the evidence we see in the real world.
Exactly. There is a short story at the end of The Number Lantern called 5 Marks to the Moon that captures this beautifully.
I love this story because it is dripping with tension for anyone who has ever stared at a chart and felt confused.
It really is. It follows two students, Maya and Theo.
Right. They are preparing a presentation for a community math night, and they've constructed this massive, colorful bar graph showing how kids at their school travel in the morning. So walking, biking, taking the bus, or riding in a car.
And Maya's checking the data, and she hits a wall.
Maya knows for a fact that 40 kids ride the bus. She gathered the data herself.
Right.
But when she looks at the yellow bar for the bus on their poster board, there are only 8 blocks stacked up. 8 physical blocks representing 40 kids.
Maya panics.
Totally. She immediately assumes the graph is broken or that the data is lying to her.
Which is such a natural reaction. When a visual representation contradicts our internal expectation, our default reaction is often mistrust.
We just assume the system is flawed.
Exactly.
But then they step back and look at the whole picture. The bar for walking has 5 blocks representing 25 kids. The biking bar has 3 blocks for 15 kids. Suddenly, the math clicks into place. 8 blocks times 5 equals 40 kids.
The graph wasn't lying.
Not at all. The little paper label that said scale, 1 block equals 5 students, had literally fallen off the poster board onto the floor.
If we connect this to the bigger picture, without the scale, a bar graph is just a colorful drawing.
It really is.
It contains no usable information until you understand what a single unit represents. Maya's initial mistake, believing the graph was wrong, is exactly what pointed her toward the missing piece of information.
The data wasn't trying to deceive them. They just had to ask the right question. What is the scale?
Think about how critical that skill is when you are an adult scrolling through your phone,
Oh man.
looking at a terrifying chart on a news broadcast, or trying to read an investment portfolio. Where does the axis begin?
Are the intervals jumping by tens or millions?
Who is actually counted?
Moving from a blind emotional reaction to structured critical thinking is the entire point. That is the journey this source takes you on.
It really does. It rescues mathematics from being a traumatic speed run of memorized tricks and restores it to its true purpose, which is a toolkit for interpreting reality.
Whether you are trying to measure out exactly 4.4 liters of lemonade for a neighborhood block party,
Right.
or setting up a mental guardrail for your grocery bill so you don't overdraw your checking account,
Exactly.
or decoding the scale on a controversial news graph. The arithmetic is just the vehicle. Understanding the relationship between the numbers is the destination.
Next time you're faced with a problem that feels overwhelming, pause and ask the core questions we've explored today.
What is known?
All right.
What has actually changed?
What unit belongs here? That analytical framework is a superpower that extends far beyond a third-grade classroom.
It forces you to engage with the world as it actually is, not just as a blur of numbers.
Which leaves us with one final provocative question to ponder.
Let's hear it.
We began by discussing how math is often introduced as a high-stress performance where errors are punished. But what if we were all conditioned from childhood to believe that a corrected mistake is the actual evidence of learning?
Wow.
How would that fundamental shift alter the way you process adult anxieties? How would it change your approach to financial planning or your patience when interpreting conflicting data in your daily life?
What if every error you make isn't a failure, but just a 5-mark clue waiting to be decoded?
It really makes you wonder.
It does. If we stopped viewing our missteps as dead ends and started viewing them as missing scale labels on the graph of our lives, well, maybe the world would look a little less like a stressful stack of tricks and a little more like a beautiful, readable language.